Picture this: billions of years ago, when the universe was still in its fiery youth, cosmic monsters were already awake. Not the kind from storybooks, but real celestial beasts so powerful they could outshine entire galaxies. These are quasars, the most energetic objects in existence, beaming their light across space and time to reach us here and now. What makes them even more incredible? We're seeing them as they were when the cosmos was just a toddler. That's right, the light from these distant quasars has traveled for over 13 billion years to land in our telescopes. And yet, despite their mind-bending power and age, they remain some of the universe's best-kept secrets. But not for long. Today, we're pulling back the curtain on these cosmic powerhouses. We've got 50 astonishing facts about quasars that will change how you see the night sky. From supermassive black holes with appetites that defy logic, to jets of matter screaming across space at nearly light speed, to the way these ancient beacons helped shape the universe itself. So buckle up. We're about to take a journey to the farthest edges of space and time, where the rules of physics get stretched to their limits, and where the universe puts on its most spectacular light show. Trust me, by the time we're done, you'll never look at a twinkling star the same way again. Now let's zoom in on what makes quasars truly extraordinary. Imagine a single object so bright that it outshines not just one star, but an entire galaxy of hundreds of billions of stars. That's exactly what quasars do. These cosmic powerhouses pump out more energy in a single second than our sun will produce in its entire lifetime. To put it in perspective, the brightest quasars can emit more light than 1 trillion suns combined. But where does all this mind-blowing energy come from? The answer lies at the heart of every quasar, a supermassive black hole, millions or even billions of times heavier than our sun. These black holes aren't just sitting quietly in space. They're actively feeding, pulling in vast amounts of gas, dust, and even stars. As this material spirals inward at nearly the speed of light, it heats up to unimaginable temperatures, glowing brighter than anything else in the universe. This process turns quasars into what astronomers call active galactic nuclei, the blazing cores of distant galaxies. And because they're so incredibly luminous, we can spot them from billions of light years away. That means when we observe a quasar, we're not just seeing a distant object, we're peering back in time, catching a glimpse of the universe when it was young and chaotic. So next time you look up at the night sky, remember, some of those faint, twinkling points of light might not be stars at all. They could be quasars, the universe's ultimate powerhouses shining across the ages. Now, let's rewind the cosmic clock to uncover how these brilliant enigmas first caught humanity's attention. In the early 1950s and 60s, astronomers scanning the skies with radio telescopes stumbled upon something peculiar: tiny, star-like objects emitting intense radio waves. At first glance, they seemed like ordinary stars, but their light told a different story. When scientists split their light into spectra, the patterns defied all expectations. The spectral lines were shifted so far toward the red end of the spectrum that they appeared alien, unlike anything seen in our own galaxy. Enter Martin Schmidt, the astronomer who cracked the code in 1963. Staring at the spectrum of a quasar known as 3C273, he made a revolutionary realization. The strange lines weren't from some unknown element, but were familiar hydrogen lines stretched by the Doppler effect. This redshift meant the object wasn't just distant, it was racing away from us at an astonishing speed, propelled by the expanding universe. Suddenly, what seemed like faint stars were revealed as cosmic beacons billions of light years away, shining from the universe's youth. The discovery sent shockwaves through astronomy. These weren't just oddball stars, they were windows into the early cosmos, powered by unimaginably massive black holes. And with that revelation, quasars transformed from celestial curiosities into some of the most important tools for understanding our universe's history. Now imagine holding a telescope that lets you peer billions of years into the past. That's essentially what quasars offer us, a cosmic time machine. Because light takes time to travel across the universe, the farther we look, the further back in time we see. And quasars, with their staggering distances, act like flickering beacons from the universe's infancy. When we observe the light from these objects, we're not just seeing distant points of energy, we're glimpsing conditions that existed when the cosmos was barely a billion years old. Think of it like uncovering an ancient fossil, but instead of bones, we're studying the raw, turbulent youth of the universe. The light from quasars carries fingerprints of the early cosmos, traces of the first heavy elements, the density of matter, even the temperature of space back then. By analyzing their spectra, astronomers can piece together how galaxies formed, how black holes grew so quickly, and how the universe transitioned from a dark, opaque sea of gas to the transparent, star-filled expanse we know today. What makes quasars especially valuable is their brightness. Even at such extreme distances, their incredible luminosity cuts through the fog of time, giving us a clear signal to study. Without them, much of what we know about the early universe would remain hidden in the shadows. So every time a quasar's light reaches us, it's not just a distant flicker, it's a message from the dawn of everything. But let's zoom in on one quasar in particular, the reigning champion of distance. Meet ULAS J1342+0928, the most distant quasar we've ever discovered. This cosmic titan sits a staggering 13 billion light-years away from us, meaning the light we see today began its journey when the universe was just 700 million years old. To put that into perspective, that's barely 5% of the universe's current age. When you look at this quasar, you're not just seeing an object far away, you're witnessing a snapshot of the universe in its toddler phase. The light from ULAS J1342+0928 has traveled across nearly the entire span of cosmic history to reach our telescopes. Every photon carries with it the secrets of an era when the first galaxies were still taking shape, and the cosmos was a far more chaotic place. What's even more mind-blowing is that this quasar isn't just distant, it's also home to a supermassive black hole weighing in at around 800 million times the mass of our Sun. That raises a fascinating question: how did a black hole grow so massive so quickly after the Big Bang? It's like finding a skyscraper in the middle of an ancient wilderness, defying our expectations of how fast cosmic structures can form. ULAS J1342+0928 isn't just a record breaker, it's a puzzle piece that challenges our understanding of the early universe. And as telescopes grow more powerful, who knows what even more distant quasars we might uncover, pushing the boundaries of what we thought was possible. Now, let's tackle one of the biggest mysteries quasars have forced us to confront: how supermassive black holes grew so enormous so early in the universe's history. These cosmic behemoths, like the 800 million solar mass monster at the heart of ULAS J1342+0928, shouldn't have had enough time to reach such staggering sizes if they grew at the rates we observe in the nearby universe. Yet quasars prove they did, and that means our textbooks might need a rewrite. One leading theory suggests these black holes didn't grow slowly by nibbling on gas over billions of years, they feasted. Imagine a cosmic buffet where entire gas clouds, or even smaller black holes, plunged into them at breakneck speeds. In the dense, chaotic environment of the early universe, mergers between galaxies could have funneled vast amounts of material straight into these black holes, supercharging their growth. Some simulations even show they might have devoured the equivalent of 1,000 suns every year, a feeding frenzy that would make them balloon in size within just a few 100 million years. But there's another twist. What if the first black holes started out big from the very beginning? Instead of forming from collapsing stars, which cap out around a few dozen solar masses, the earliest black holes might have been born heavyweight. Collapsing clouds of primordial gas, untouched by heavy elements, could have directly collapsed into black holes thousands of times more massive than the Sun. These seed black holes would then have a head start, making it easier to explain how quasars became so luminous so quickly. Quasars don't just show us that supermassive black holes existed early, they force us to rethink how the universe builds them. Whether through insatiable appetites or colossal beginnings, these objects defy our expectations, and that's what makes them such thrilling puzzles. As we peer deeper into the past with next-generation telescopes, we might finally uncover which of these wild theories, or perhaps something even stranger, holds the key to their rapid rise. Now, let's zoom in on one of the most visually stunning features of quasars, their high-speed jets. Picture a cosmic fire hose blasting out particles at nearly the speed of light, stretching hundreds of thousands of light years into space. These jets are so powerful they can punch through entire galaxies, leaving behind glowing trails known as radiolobes. What makes these jets even more fascinating is how relativity comes into play. Because the particles are moving so close to the speed of light, strange things happen to our observations. For instance, if a jet is pointed almost directly at us, it can appear to move faster than light, an illusion caused by the jet's material racing toward us at a slight angle, compressing the light waves and making it seem unnaturally speedy. These jets aren't just for show, they're cosmic power lines, channeling energy from the quasar's supermassive black hole into the surrounding universe. They heat up interstellar gas, trigger star formation in some regions, and even suppress it in others, shaping the evolution of galaxies in ways we're only beginning to understand. And here's the kicker: sometimes these jets flicker or flare unpredictably, giving us clues about the chaotic environment right at the edge of the black hole. It's like watching a lighthouse beam from across the universe, with each pulse revealing secrets about the engine powering it. Now, let's untangle a cosmic case of mistaken identity quasars and their close relatives blazars. At first glance, they might seem like the same phenomenon, but the key difference lies in how they're angled toward us. Picture a flashlight. If you're staring straight into the beam, it's blindingly bright. That's a blazar. But if the flashlight is tilted slightly away, the light appears less intense, and that's more like a typical quasar. Blazars are essentially quasars with a twist. Their jets are pointed almost directly at Earth. This alignment amplifies their brightness and makes their emissions appear more violent, often flickering unpredictably across the electromagnetic spectrum. Because we're staring down the barrel of their particle jets, blazars outshine even the most luminous quasars, despite being powered by similar supermassive black holes. Meanwhile, quasars viewed from a wider angle let us see more of their structure, like their glowing accretion disks and the faint glow of their host galaxies. This difference in perspective isn't just about appearances, it changes how we study them. Blazars with their head-on jets are laboratories for extreme physics, revealing how matter behaves at near light speeds. Quasars, on the other hand, offer a broader cosmic census, helping us map the distribution of supermassive black holes across the universe. Here's the fascinating part: a single active galaxy could appear as a blazar to one observer and a quasar to another, depending on their vantage point in the cosmos. It's a reminder that what we see in the universe often depends on where we're standing, or in this case, where Earth happens to be looking from. Now, let's step back in time to an era when the universe was a very different place, a shadowy expanse known as the Cosmic Dark Ages. This was a period before stars and galaxies had fully formed, when the universe was filled with neutral hydrogen gas, blocking light from traveling freely. But then came quasars, acting like cosmic lighthouses that pierced through the gloom. These brilliant beacons didn't just illuminate the early universe, they transformed it. The intense radiation from quasars ripped electrons away from hydrogen atoms in a process called ionization, turning the opaque fog of neutral gas into a transparent sea of charged particles. This monumental shift, known as reionization, marked the end of the Dark Ages and allowed light to travel unimpeded across the cosmos for the first time. But quasars didn't stop there. Their energy didn't just ionize the gas, it heated it to staggering temperatures, sometimes reaching millions of degrees. This superheated intergalactic medium became a dynamic backdrop for galaxy formation, influencing how and where stars could eventually take shape. Think of it like a cosmic oven where quasars turned up the heat, altering the very conditions that would dictate the universe's future structure. What's truly remarkable is the scale of their impact. Even though quasars were relatively rare, their energy traveled vast distances, creating vast bubbles of ionized gas that eventually overlapped and merged. This wasn't just a local phenomenon, it was a universe-wide metamorphosis driven by some of the most powerful objects in existence. Without quasars, the cosmos might have remained shrouded in darkness far longer, delaying the birth of the vibrant universe we see today. So the next time you gaze at the night sky, remember, those distant points of light aren't just fascinating oddities, they were the architects of cosmic dawn. Now, let's shift our focus to an unexpected role quasars play in mapping the cosmos, acting as cosmic measuring sticks. You might think their wild fluctuations in brightness would make them unreliable for distance calculations, but astronomers have found clever ways to turn these unpredictable beacons into tools for measuring the vast stretches of the universe. The idea hinges on a concept called the standard candle, an object with a known intrinsic brightness that lets scientists gauge how far away it is based on how dim it appears from Earth. While quasars don't have a fixed brightness like traditional standard candles, their variability itself holds clues. Researchers have discovered patterns in how their light changes over time, allowing them to estimate distances by analyzing these flickers. It's like deciphering the rhythm of a distant lighthouse to determine how far its glow has traveled. Of course, using quasars this way isn't without challenges. Their erratic behavior means measurements require painstaking analysis, and early attempts often led to conflicting results. But breakthroughs in machine learning and larger datasets have refined the process, turning quasars into valuable markers for probing the universe's expansion. Some studies even suggest they could help resolve the ongoing debate about the Hubble constant, the rate at which the cosmos is stretching apart. What's fascinating is how this transforms our view of quasars. They're not just dazzling anomalies or relics of the early universe, they're also keys to unlocking the geometry of space itself. As telescopes grow more powerful and methods more precise, these distant giants may yet reveal secrets about the fabric of reality we've only begun to imagine. Now let's journey even further back in time, to the very dawn of quasars. Picture the universe in its infancy, just a few 100 million years after the Big Bang. In this chaotic, energetic era, the first quasars flickered to life, their supermassive black holes already weighing in at billions of times the mass of our Sun. How these cosmic giants grew so massive so quickly remains one of astronomy's greatest puzzles. One leading theory suggests they feasted on vast reservoirs of gas in the dense early universe, or perhaps they were born from the direct collapse of enormous primordial gas clouds, skipping the usual star-forming stage entirely. Either way, their existence challenges our understanding of black hole formation, forcing scientists to rethink the limits of cosmic growth. Today, astronomers hunt for these primordial quasars like cosmic archaeologists, sifting through data from telescopes like the James Webb Space Telescope. Every new discovery, like the Quasar J1342+0928, which existed when the universe was just 670 million years old, offers clues about how the first structures in the cosmos took shape. Finding even earlier examples could reveal the conditions that allowed black holes to dominate so soon after the universe's birth. What's thrilling is that we're on the brink of uncovering more of these ancient beacons. With each technological leap, we peer closer to the cosmic dawn, inching toward the moment when the very first quasar ignited and rewrote the story of our universe. Now let's turn our attention to something equally fascinating: the flickering glow of quasars themselves. These cosmic powerhouses don't shine with a steady light. Instead, they flicker and flare, sometimes brightening or dimming over days, weeks, or even years. This unpredictable dance of light isn't just random. It's a window into the chaotic environment near a supermassive black hole. The key to understanding these variations lies in the accretion disk, the swirling maelstrom of gas and dust feeding the black hole. As material spirals inward, it heats up to millions of degrees, glowing brilliantly before vanishing beyond the event horizon. But this process isn't smooth. Clumps of gas collide, magnetic fields twist and snap, and shockwaves ripple through the disk, causing sudden bursts of energy. These disruptions create the flickering patterns we observe, like cosmic fireworks erupting in slow motion. What's truly remarkable is how much these light curves reveal. Rapid changes in brightness, sometimes occurring in just hours, tell us the emission is coming from an incredibly compact region, no larger than our solar system. That's mind-boggling when you consider the energy output rivals entire galaxies. Slower, long-term variations, on the other hand, might hint at changes in the black hole's feeding rate or even the influence of companion black holes in binary systems. Astronomers meticulously track these fluctuations, using them to map the structure of accretion disks and test theories about black hole physics. It's like decoding the heartbeat of a quasar, each pulse and dip a clue to the violent, high-stakes drama unfolding at the edge of spacetime. And with new telescopes capturing more detailed light curves than ever, we're closer than ever to unraveling the secrets behind these cosmic light shows. Now, here's something that might surprise you: quasars don't light up in isolation. Their fiery brilliance is often sparked by cosmic collisions. When galaxies smash into each other, the chaos doesn't just reshape stars and dust, it supercharges the supermassive black holes at their cores. Think of it like a cosmic traffic jam where gas and stars get funneled toward the center, piling onto the black hole's plate. These galactic mergers are like all-you-can-eat buffets for quasars. As two galaxies intertwine, their gravitational dance sends massive amounts of gas spiraling inward, cramming the accretion disk until it overheats and erupts in a blaze of light. One stunning example is the quasar Markarian 231, nestled in a galaxy that's clearly the product of a violent merger. Its twisted arms and turbulent core tell the story of a recent collision, with the quasar blazing at the heart of the wreckage. But it's not just about spectacle. These mergers solve a puzzle. How do supermassive black holes grow so fast in the early universe? Collisions provide the answer, delivering fuel at breakneck speed. Take the system known as NGC 624, where two smaller black holes, each the remnant of a devoured galaxy, now orbit each other, destined to merge and ignite another quasar. What's wild is that we're catching these events in action. Telescopes like Hubble have snapped images of galaxies mid-collision, their cores flickering to life as quasars awaken. It's a reminder that in the cosmos, destruction and creation are two sides of the same coin, and quasars are the dazzling proof. Now, let's tackle one of the biggest head-scratchers about quasars: how do they keep their engines running at full blast? These cosmic beacons don't just flicker out after a quick burst. They shine brilliantly for millions of years, and that demands an almost unimaginable amount of fuel. So where does it all come from? The secret lies in the chaotic dance of matter around the supermassive black hole at the quasar's heart. Picture a whirlpool of gas and dust swirling faster and faster as it gets closer to the edge of the black hole. This spinning disk, called an accretion disk, is where the magic happens. The material in the disk doesn't just fall straight in, it spirals inward, heating up to millions of degrees from sheer friction and gravitational pressure. That's what turns the disk into a glowing, white-hot powerhouse, pumping out the insane amounts of light and energy we see from Earth. But here's the twist: not everything in the disk gets swallowed. Some of the material gets flung outward in jets or blown away by intense radiation pressure. It's a messy, inefficient process, and yet quasars still manage to convert a staggering amount of mass into energy. Scientists estimate that to keep a quasar shining, its black hole needs to devour the equivalent of 10 stars every year. That's like swallowing our entire sun 10 times over annually. And the physics gets even wilder. As matter nears the black hole, time itself starts to warp. The intense gravity slows down time for the infalling material from our perspective, making it seem like the disk's inner edge flickers in slow motion. Meanwhile, magnetic fields twist and snap, channeling some of the material into those high-speed jets we've talked about before. It's a cosmic balancing act, one that keeps quasars burning bright across the ages. So next time you hear about a distant quasar, remember, it's not just a black hole's appetite that makes it shine. It's the entire frenzy of physics around it, turning destruction into light on a scale we can barely fathom. Now, let's peel back another layer of the quasar mystery, their surprising connection to the invisible glue of the cosmos, dark matter. While quasars blaze with light, their existence might hinge on something we can't even see. Dark matter, that elusive substance making up most of the universe's mass, could be the hidden architect behind these brilliant beacons. Here's how it works. Galaxies, including the ones hosting quasars, are thought to be nestled within vast halos of dark matter. These halos act like gravitational scaffolds, holding galaxies together and funneling gas toward their centers. Without this invisible framework, galaxies might not have enough structure to feed their central black holes consistently. In other words, dark matter could be the silent partner in the quasar's energy production, ensuring a steady supply of fuel over cosmic timescales. But the plot thickens. Some theories suggest that the most luminous quasars might be linked to the densest dark matter halos in the early universe. These regions would have pulled in more gas, creating ideal conditions for supermassive black holes to grow rapidly and ignite as quasars. It's a cosmic feedback loop. Dark matter shapes the galaxy feeds the black hole, and the quasar lights up, potentially even influencing how dark matter distributes itself over time. And there's a tantalizing clue from simulations. When scientists model the universe's evolution, they find that quasars often appear where dark matter filaments intersect, like glowing knots in a cosmic web. This alignment hints that dark matter doesn't just host quasars, it might guide their formation, placing them at the crossroads of the universe's largest structures. So while dark matter remains invisible, its gravitational fingerprints are all over the quasar phenomenon. Next time you marvel at one of these distant powerhouses, remember, its brilliance might owe as much to the shadows as to the light. Now let's zoom in on the galaxies that serve as the cosmic homes for these dazzling quasars. Picture a quasar's host galaxy as a bustling metropolis, with the supermassive black hole at its center acting like a hyperactive power plant. These galaxies aren't your typical spirals like our Milky Way. They're often massive ellipticals, shaped like giant footballs, or chaotic, disturbed systems still reeling from violent collisions. What's fascinating is how a single quasar can outshine its entire host galaxy, sometimes by a factor of 100 or more. Imagine a tiny light bulb so bright it drowns out the glow of an entire city. That's the scale we're talking about. The quasar's brilliance comes from the frenetic activity just outside the black hole's event horizon, where gas spirals inward at nearly the speed of light, heating up to millions of degrees and glowing fiercely. Meanwhile, the rest of the galaxy's stars, though numerous, simply can't compete with that concentrated fury. But here's the twist: the host galaxy isn't just a passive backdrop. These galaxies are often stuffed with gas and dust, the raw materials that feed the quasar's insatiable black hole. Some show signs of recent mergers, their shapes twisted by gravitational encounters that funnel fuel toward the center. Others might be red and dead ellipticals where star formation has mostly ceased, leaving the quasar as the primary source of light. This dynamic raises a cosmic irony. The very galaxies that nurture quasars are often rendered invisible by them. Astronomers sometimes struggle to detect the host at all, its starlight washed out by the quasar's glare. It's only with advanced telescopes and clever techniques like blocking the quasar's light that we've begun to unveil these shadowed giants. So while quasars steal the spotlight, their host galaxies play a crucial, if understated, role in the drama. They're the stages on which these cosmic fireworks unfold, proving that even in the universe, the brightest stars, or in this case, black holes, don't shine alone. Now, let's take a detour into one of nature's most fascinating cosmic tricks, gravitational lensing, and how it gives us an even closer look at quasars. Imagine light from a distant quasar traveling across the universe for billions of years, only to be bent and warped by the gravity of a massive galaxy or cluster in its path. This cosmic mirage doesn't just distort the quasar's image, it can magnify it, acting like a natural telescope that brings the distant object into sharper focus. One of the most famous examples is the Einstein cross, a quasar whose light is split into 4 distinct images by the gravitational pull of a foreground galaxy. It's like holding up a kaleidoscope to the universe, where a single quasar appears multiplied, each image a slightly altered version of the original. Another standout is the double quasar, discovered in the 1970s, which turned out to be 2 images of the same quasar, bent by an intervening galaxy. These lensed systems aren't just cosmic curiosities, they're gold mines for astronomers. By studying these magnified quasars, scientists can peer into regions that would otherwise be too small or faint to see. The lensing effect can reveal details about the quasar's inner structure, like the size of its accretion disk or the motion of gas near the black hole. It even lets us probe the lensing galaxy itself, helping us map out how dark matter is distributed in these cosmic giants. Gravitational lensing also gives us a rare opportunity to test Einstein's theory of relativity on galactic scales. The way light bends around massive objects matches his predictions with stunning precision, proving once again that the universe is the ultimate laboratory for physics. So while quasars are already cosmic beacons, gravitational lensing turns them into something even more extraordinary, a window into the unseen forces shaping the universe. And with new telescopes coming online, we're bound to discover even more of these cosmic magnifying glasses, bringing the farthest quasars into clearer view than ever before. Now, let's shift our gaze to another incredible tool quasars give us: their absorption lines. When we study the light from a quasar as it travels across the universe, it doesn't arrive untouched. Along the way, it passes through vast clouds of gas, and these clouds leave their fingerprints on the quasar's spectrum in the form of dark absorption lines. Think of it like holding a prism up to sunlight and seeing the rainbow, except here, the missing colors tell us what's floating in the space between us and the quasar. These absorption lines act like a cosmic barcode, revealing the composition, temperature, and even the motion of the gas clouds that intercept the quasar's light. Some of these clouds are pristine, containing mostly hydrogen and helium remnants from the early universe. Others are laced with heavier elements like carbon and oxygen, hinting at past generations of stars that lived and died, seeding the cosmos with their remains. What's truly remarkable is how these lines let astronomers map the universe's large-scale structure. By analyzing thousands of quasar spectra, scientists can trace the distribution of gas across billions of light years, uncovering the filamentary web that connects galaxies. It's like taking a core sample of the cosmos, drilling through space and time to see how matter is woven together. One of the most famous examples is the Lyman Alpha Forest, a dense thicket of absorption lines caused by hydrogen clouds. Each line represents a different distance, creating a layered record of the universe's history. By decoding this forest, researchers can study how the cosmos evolved, from the chaotic early epochs to the more structured universe we see today. So next time you hear about a quasar's spectrum, remember it's not just a beam of light. It's a messenger carrying secrets from every cloud it's passed through, helping us piece together the story of everything. Now let's unravel another fascinating layer of quasars, their classification. Just like stars follow a main sequence based on their temperature and brightness, quasars have their own version of this cosmic ordering system. Scientists call it the quasar main sequence, and it's a powerful tool for understanding how these luminous beasts behave. At its core, the quasar main sequence sorts these objects based on two key features: their emission lines and their accretion rates. Emission lines are the bright or dark fingerprints in a quasar's spectrum, revealing the elements and conditions near the black hole. Some quasars show strong, broad emission lines, while others have narrower, fainter ones. This difference isn't random, it's tied to how fast material is spiraling into the black hole. Quasars with high accretion rates, meaning they're guzzling gas at a furious pace, tend to have broader, more turbulent emission lines. Their black holes are feasting so intensely that the surrounding gas gets heated to extreme temperatures, creating a chaotic, high-energy environment. On the other end, quasars with lower accretion rates have calmer, narrower lines, hinting at a more subdued meal. But here's where it gets even more interesting. The main sequence also reveals a quasar's orientation relative to us. Some quasars appear brighter because we're looking straight down the barrel of their jets, while others are seen from the side, offering a different spectral profile. This means the main sequence isn't just about appetite, it's also about perspective. By mapping quasars along this sequence, astronomers can decode their life cycles, from ravenous youth to quieter maturity. It's like sorting a cosmic zoo into categories, helping us predict how these objects evolve over billions of years. So next time you hear about a quasar's spectrum, remember, it's not just light. It's a storybook, and the main sequence is its table of contents. Now, let's step back in time to one of the most dramatic transformations in cosmic history, the era of reionization. Picture the early universe like a thick fog, filled with neutral hydrogen gas that absorbed ultraviolet light, keeping everything shrouded in darkness. But then, quasars stepped onto the scene, acting like cosmic blowtorches that burned away this fog and lit up the universe as we know it today. Here's how it happened. After the Big Bang, the universe cooled enough for protons and electrons to combine into neutral hydrogen, creating a kind of cosmic haze. For hundreds of millions of years, this gas blocked ultraviolet light, leaving the universe in what astronomers call the Dark Ages. But then, the first quasars and galaxies began to flicker on, and their intense radiation started ionizing the hydrogen, knocking electrons loose and turning it back into a transparent plasma. Quasars were especially powerful players in this process. Their supermassive black holes pumped out torrents of ultraviolet and X-ray light, carving vast bubbles of ionized gas around them. Over time, these bubbles grew and merged like holes melting through a sheet of ice until the entire universe became transparent to ultraviolet light. This was the epoch of reionization, and it fundamentally changed how light could travel through space. But here's the twist: quasars didn't act alone. While they were the brightest ionizing sources, they were also relatively rare. Most of the heavy lifting was likely done by countless smaller galaxies, their collective starlight adding to the reionization effort. Yet quasars were the powerhouses that pushed the process forward in their immediate surroundings, leaving behind a universe where light could finally travel freely. So when we look at the most distant quasars, we're not just seeing ancient beacons, we're witnessing the architects of cosmic clarity. Their light, now billions of years old, carries echoes of the moment the universe woke up from its dark slumber and became the transparent, luminous expanse we explore today. Now let's zoom in on one of the most mind-bending abilities of quasars, their power to act as nature's ultimate particle accelerators. These cosmic giants don't just emit light, they launch jets of charged particles at velocities so close to the speed of light that they rival the most advanced machines we've built on Earth. Here's how it works. When matter spirals into a quasar's supermassive black hole, not all of it gets swallowed. Some particles get funneled into powerful magnetic fields and shot outward in narrow beams, traveling millions of light years into space. These jets are so energetic that they can accelerate electrons and protons to energies far beyond what even the Large Hadron Collider can achieve. But the real cosmic twist: these particles might be the source of some of the most mysterious phenomena in the universe: ultra-high-energy cosmic rays. These are subatomic bullets traveling through space with energies millions of times greater than anything we can produce in labs. For decades, their origins puzzled scientists, but quasars are now prime suspects. When their jets collide with intergalactic gas or magnetic fields, they could be launching these extreme particles across the cosmos. What's even wilder is that some quasars might be firing neutrinos, ghostly particles that barely interact with matter, straight at Earth. Detectors like IceCube in Antarctica have picked up high-energy neutrinos that trace back to distant quasars, offering tantalizing clues about the violent processes happening near their black holes. So next time you hear about a cosmic ray or a neutrino detection, remember, it might have started its journey in the heart of a quasar billions of years ago. These celestial accelerators aren't just lighting up the universe, they're hurling pieces of themselves across space and time, giving us a front-row seat to some of the most extreme physics in existence. Now, let's step back in time to an era when quasars ruled the cosmos, the quasar epoch. Picture the universe roughly 10 billion years ago, a time when these brilliant beacons were at their most active, lighting up the darkness like cosmic fireworks. This was the golden age of quasars, when they were far more numerous and energetic than they are today. Back then, the universe was a much denser place, packed with young galaxies brimming with gas, the perfect fuel for supermassive black holes. Collisions between galaxies were common, funneling vast amounts of material into their cores and igniting quasar outbursts. In fact, during this peak period, quasars were hundreds of times more abundant than they are now, turning the early universe into a dazzling spectacle of light and energy. But why did this era fade? As the universe expanded, galaxies grew farther apart, and the gas reservoirs that fed quasars began to dry up. Without fresh material to devour, many supermassive black holes quieted down, leaving behind the more subdued universe we see today. Yet, even now, the light from those ancient quasars continues to reach us, carrying clues about this explosive chapter in cosmic history. The quasar epoch wasn't just a flashy phase, it was a turning point. These luminous giants didn't just shine, they shaped the universe around them, heating intergalactic gas, seeding galaxies with heavy elements, and even influencing how stars formed. So when we look at distant quasars today, we're not just seeing relics of the past, we're witnessing the architects of the cosmos in their prime. Now, let's uncover one of the most fascinating ways quasars shape their surroundings, through something called quasar feedback. Imagine a cosmic balancing act where these brilliant behemoths don't just consume material but also give back in dramatic fashion. Here's how it works. As a quasar's supermassive black hole feasts on gas and dust, it doesn't just sit quietly, it blasts out enormous winds and jets at nearly the speed of light. These outflows are so powerful they can sweep across entire galaxies, pushing away the very gas clouds that would otherwise collapse to form new stars. It's like a cosmic thermostat where the quasar's fury prevents its host galaxy from becoming too crowded with stars. This feedback mechanism is crucial because it solves a long-standing puzzle. Without it, many galaxies would grow far larger and brighter than what we actually observe, but quasars, in their explosive brilliance, keep things in check. They heat up or eject gas, starving future star formation and ensuring galaxies don't overindulge. What's truly mind-blowing is the scale of this process. Some quasar-driven winds can travel tens of thousands of light-years, reshaping not just their host galaxies but the surrounding intergalactic space. So while quasars might seem like cosmic destroyers, they're actually master regulators sculpting galaxies into the diverse shapes and sizes we see today. This delicate dance of creation and destruction highlights just how interconnected the universe really is. Quasars don't just light up the cosmos, they help write the rules of galactic evolution. But here's something curious: quasars weren't always as rare as they are today. In fact, the universe used to be absolutely buzzing with them. So what happened? Why did these brilliant beacons start fading away? The answer lies in their fuel supply. Remember, quasars shine because supermassive black holes gorge on gas and dust. But over billions of years, that cosmic buffet began running low. Galaxies, once rich with fresh material from collisions and chaotic mergers, gradually settled down. Without a steady influx of gas to feed their black holes, quasars dimmed, their fiery brilliance fading into quiet obscurity. Think of it like a campfire running out of wood. Even the most intense flames eventually dwindle when there's nothing left to burn. For quasars, the same principle applies. Their incredible energy output depends entirely on having enough material to devour. As the universe aged, galaxies grew more orderly, collisions became rarer, and the gas reservoirs near black holes were either consumed or blown away by those very quasars themselves. This decline wasn't sudden, though. Quasar activity peaked around 10 billion years ago, then tapered off as the cosmos matured. Today, we mostly see their quieter descendants, galaxies with dormant black holes, their glory days long past. But every now and then, a flicker of that old brilliance returns when a fresh supply of gas drifts too close, briefly reigniting the quasar's flame. So while the golden age of quasars may be over, their legacy lives on. They shaped the galaxies we see today, then quietly stepped back, leaving behind a universe that's a little calmer, but no less fascinating. Now let's zoom out and see quasars in their grandest context, the cosmic web. Picture the universe not as a random scatter of galaxies, but as an intricate network of glowing threads, like a spider's silk stretched across the void. Quasars aren't just floating anywhere, they're perched at the busiest crossroads of this vast structure, where cosmic filaments intersect. These filaments, made of dark matter and gas, form the skeleton of the universe, guiding galaxies into clusters and superclusters. And quasars, they're the blazing signposts marking the densest knots in this web. Their supermassive black holes didn't grow in isolation. They thrived where the universe funneled the most fuel, right at these bustling intersections. What's fascinating is that quasars don't just sit there, they reveal the web itself. Their light pierces through the gas along these filaments, allowing astronomers to map the invisible scaffolding of the cosmos. It's like turning on a flashlight in a foggy forest. The beams show you the hidden paths. So next time you hear about a distant quasar, remember, it's not just a cosmic oddity. It's a beacon illuminating the universe's hidden architecture, showing us where the grand highways of matter meet. And that's a story written in light across billions of years. Now let's pull back the curtain on one of the most jaw-dropping aspects of quasars, the sheer size of the monsters at their cores. Measuring the mass of a supermassive black hole sounds like science fiction, but astronomers have clever ways to weigh these cosmic giants. By studying how stars and gas whip around the black hole's gravitational grip, or analyzing the flickering light from its accretion disk, scientists can calculate its mass with surprising precision. And here's where things get mind-bending. The black holes powering quasars aren't just big, they're unfathomably massive. We're talking billions of times heavier than our sun. To put that in perspective, imagine squeezing the mass of every star in our Milky Way into a single point smaller than our solar system. That's the kind of gravitational titan we're dealing with. What's even wilder, these black holes didn't start out this enormous. They grew by devouring gas, dust, and even entire stars over billions of years. But here's the puzzle. Some quasars in the early universe had supermassive black holes when the cosmos was barely a toddler. How did they bulk up so fast? That's one of the biggest mysteries in astrophysics today. So next time you gaze at a quasar's brilliant light, remember, it's not just a distant spark. It's the signature of a gravitational behemoth, a black hole so massive it bends the very fabric of space around it. And thanks to some brilliant cosmic detective work, we're slowly unraveling the secrets of how these giants came to rule the universe. Now let's zoom in on one of the quirkiest behaviors of quasars, their habit of flickering like cosmic light bulbs. These brightness changes aren't random. They're actually cosmic stopwatches revealing secrets about the black holes at their hearts. When a quasar's light fluctuates over days, weeks, or even hours, it tells astronomers something extraordinary. The source of that light must be incredibly tiny. Think of it like this: if you tried to make a stadium-sized light bulb flicker in unison, it'd be impossible. The far side wouldn't get the memo in time. But a quasar's rapid shifts mean its light comes from a region so compact, signals can cross it almost instantly. That points to a space no bigger than our solar system, where matter swirls at nearly light speed just outside the black hole's event horizon. Some quasars even pull off brightness changes in mere hours, a blink of an eye in cosmic terms. That's like spotting a glow in the dark sticker on Pluto from Earth, then watching it pulse like a strobe light. These lightning-fast variations are smoking gun evidence that quasars pack their unbelievable energy into unthinkably small spaces, all governed by the black hole's crushing gravity. So next time you hear about a quasar's flicker, remember, it's not just a light show. It's a cosmic breadcrumb trail leading us straight to the edge of space-time itself. Now let's turn our gaze back to the cosmic dawn, when the first stars flickered to life in a pitch-black universe. These weren't just any stars, they were population 3 stars, the universe's original giants, and they might hold the key to how quasars got their start. Picture this, a universe so young that not a single galaxy existed yet, just vast clouds of pristine hydrogen and helium. Within those clouds, gravity sculpted the first stars, monsters hundreds of times heavier than our sun, burning ferociously and dying young in spectacular supernovas. Here's where quasars enter the story. When these primordial stars exploded, they could have left behind the seeds of supermassive black holes, collapsing directly into black holes or merging in dense stellar nurseries. Over time, these black holes gorged on gas and grew at breakneck speeds, possibly becoming the engines of the first quasars. It's like finding a fossil and realizing it belonged to an ancestor of modern creatures, except here, the fossils are quasars, and their ancestors were stars that lived and died before Earth even existed. But the connection might go deeper. Population 3 stars were factories for heavier elements, and their deaths littered space with the raw materials for future stars and planets. Some theories suggest quasars helped distribute these elements, acting as cosmic mixers in the early universe. Imagine a quasar's jet blasting newly forged carbon and oxygen across space, sprinkling the ingredients for life into the void. While we've yet to spot a population 3 star directly, quasars might be our best clues to understanding them. Their light, traveling for billions of years, carries fingerprints of the early universe's chemistry, hints about those first fleeting giants. So when we study the most distant quasars, we're not just looking at black holes, we're glimpsing the aftermath of the universe's very first starlight. Now let's shift our focus to something equally mind-blowing: the hurricane force winds unleashed by quasars. These aren't your everyday breezes. We're talking about cosmic gales roaring at millions of miles per hour, fierce enough to reshape entire galaxies. Picture a supermassive black hole at the heart of a quasar. devouring matter with such ferocity that it doesn't just swallow everything, it spits part of it back out in colossal, high-speed winds. These quasar winds are like cosmic blowtorches, carving through space with enough energy to push gas and dust clear out of their host galaxies. Imagine a storm so powerful it could strip away the raw materials for future stars, effectively putting the brakes on a galaxy's ability to grow. That's exactly what astronomers think happens. Quasar winds act as a cosmic stop sign, regulating how big a galaxy can get by blowing away its star-forming fuel. But here's where it gets even wilder. These winds don't just vanish into the void. They carry heavy elements forged in the quasar's furnace, scattering them across intergalactic space like seeds in a cosmic windstorm. Over billions of years, this process might have helped enrich the universe with the building blocks for planets and even life, and the speeds they defy imagination. Some quasar winds have been clocked at 20% the speed of light. That's fast enough to travel from Earth to the Moon in less than 7 seconds. At that velocity, these winds don't just nudge their surroundings. They slam into them with enough force to trigger shock waves, heating gas to millions of degrees and lighting up the cosmos like a neon sign. So the next time you hear about a quasar, remember, it's not just a beacon of light. It's a cosmic force of nature, sculpting the universe one galactic wind at a time. Now, let's zoom out even further and consider how quasars don't just shape their own galaxies, they leave their mark on the vast, empty stretches between them. The intergalactic medium, that seemingly barren space separating galaxies, isn't as empty as you might think. Thanks to quasars, it's actually laced with heavy elements like carbon, oxygen, and iron, ingredients crucial for building planets and ultimately life. Here's how it happens. Those ferocious quasar winds we just talked about, they don't stop at the edges of their host galaxies. They blast outward, carrying atoms forged in the hearts of stars and supermassive black holes, scattering them like cosmic breadcrumbs across millions of light years. Think of it as a galactic-scale sprinkler system, spraying enriched gas into regions that would otherwise be pristine hydrogen left over from the Big Bang. This process is more than just space pollution. It's a vital part of cosmic recycling. Without quasars pumping heavy elements into the intergalactic medium, the universe would lack the raw materials needed for rocky planets, organic molecules, or even the chemistry that makes life possible. And because quasars were especially active in the early universe, they likely played a starring role in seeding the cosmos with these essential building blocks long before our solar system even existed. But here's the twist: this enrichment isn't uniform. Quasar winds create intricate webs of heavy elements, threading through the cosmos in patterns that mirror the large-scale structure of the universe itself. Astronomers can actually map these trails by studying the light from distant quasars as it passes through these enriched regions, revealing a hidden tapestry of matter woven by quasars over billions of years. So the next time you gaze at the night sky, remember those dark voids between the stars aren't so empty after all. They're a silent testament to the lasting influence of quasars, the universe's ultimate alchemists. Now, let's turn our attention to a fascinating cosmic relative of quasars' Seyfert galaxies. These celestial objects might not shine as brightly as their quasar cousins, but they hold crucial clues about the life cycle of active galactic nuclei. Picture quasars as the blazing superstars of the universe, while Seyfert galaxies are their quieter, more subdued siblings. Both are powered by supermassive black holes feasting on surrounding gas, but the difference lies in their appetites and their visibility. Quasars are so luminous they outshine entire galaxies, making their host galaxies nearly invisible in their glare. Seyfert galaxies, on the other hand, let their galactic structures take center stage, with their active cores glowing noticeably but not overwhelmingly. This distinction isn't just about brightness, it's about evolution. Many astronomers believe Seyfert galaxies represent an earlier or later phase in the life of an active galactic nucleus, depending on how much fuel is available for the central black hole. When a galaxy has plenty of gas and dust to feed its black hole, it can flare up as a quasar, blasting out incredible amounts of energy. But as the fuel runs low, the fireworks dim, and the active nucleus transitions into a safer galaxy. In some cases, the opposite might happen. Galactic collisions or other disruptions could funnel fresh gas toward a dormant black hole, reigniting it and potentially turning a safer into a quasar. What's truly intriguing is that both types of objects help us piece together the story of how supermassive black holes grow and influence their surroundings. By studying Seyfert galaxies, astronomers get a closer look at the mechanics of accretion disks and jets without the blinding glare of a full-blown quasar. It's like comparing a bonfire to a wildfire. Both teach us about combustion, but one lets us see the flames up close. So while quasars steal the spotlight with their extreme brilliance, Seyfert galaxies offer a quieter, yet equally important perspective on the dynamic lives of active galactic nuclei. Together, they show us that even in the cosmos, there's more than one way for a black hole to make its presence known. Now, let's dive into one of the most explosive connections in the cosmos: quasars and gamma-ray bursts. While quasars are known for their steady, brilliant glow, there are rare moments when they might unleash something even more extreme: gamma-ray bursts, the most powerful explosions in the universe. These bursts pack more energy in a few seconds than our sun will emit in its entire lifetime, and when they come from quasars, it's like a cosmic fireworks show on steroids. Scientists suspect these outbursts could happen when a quasar's supermassive black hole devours something massive, like a star ripping it apart in a violent tidal disruption event. The debris spirals inward at incredible speeds, heating up and triggering a jet of particles moving close to the speed of light. If that jet happens to be pointed straight at Earth, we might catch a fleeting but mind-blowing gamma-ray burst alongside the quasar's usual light. What makes this even wilder is that gamma-ray bursts from quasars could be mixed signals. Sometimes what looks like a burst might actually be two separate events: a quasar's usual activity and a distant gamma-ray burst just happening to align in the same patch of sky. Untangling these cosmic coincidences is like figuring out whether two lightning strikes hit the same place at the same time. But when quasars do produce genuine gamma-ray bursts, it's a goldmine for astronomers. These events offer clues about how black holes behave under extreme conditions, how matter behaves at near-light speeds, and even how the universe distributes its most violent energy. It's a reminder that even the brightest, most stable objects in the cosmos can have moments of unimaginable fury. So next time you hear about a gamma-ray burst, remember, it might just be a quasar's way of reminding us that even the universe's most dazzling beacons have an explosive side. Now let's zoom in on a cosmic trick of the light quasar microlensing. Imagine you're looking at a quasar billions of light years away, but suddenly its brightness flickers or spikes. That's not the quasar acting up. It's likely a star in a galaxy much closer to us passing in front of it, bending and magnifying its light like a cosmic magnifying glass. This phenomenon, called microlensing, doesn't just create a cool light show. It's a powerful tool for astronomers to peek into the quasar's hidden structure. Here's how it works. When a star in a foreground galaxy aligns perfectly between us and the quasar, its gravity warps space-time, creating a lens that amplifies the quasar's light. But because stars are tiny compared to entire galaxies, the effect is subtle and short-lived, hence micro-lensing. These fleeting brightening events can reveal details about the quasar's accretion disk, the swirling maelstrom of superheated gas feeding the central black hole. By studying how the light changes during microlensing, scientists can map the disk size, temperature, and even how matter moves around the black hole. What's even wilder is that microlensing can expose the fine print of the quasar's environment. Sometimes multiple stars in the foreground galaxy lens the quasar simultaneously, creating a complex pattern of brightness changes. Untangling these signals is like deciphering a cosmic fingerprint, helping astronomers distinguish between the quasar's core, its jets, and surrounding clouds of gas. And here's the kicker: because microlensing depends on the precise alignment of stars, it's a rare and unpredictable event. But when it happens, it turns a distant quasar into a cosmic lab, letting us test theories about black hole physics with precision we'd never get otherwise. So next time a quasar's light dances unpredictably, remember, it might just be a star in the foreground, handing us a magnifying glass to explore the universe's most extreme environments. Now, let's shift our gaze to one of the biggest puzzles in modern cosmology, the Hubble constant, and how quasars are helping us crack it. You've probably heard that the universe is expanding, but measuring how fast that's happening has turned into a cosmic tug of war among scientists. Enter quasars, the universe's distant beacons, offering a fresh way to settle the debate. Here's the scoop: the Hubble constant is the number that tells us how quickly the cosmos is stretching apart. But here's the twist: different methods keep giving slightly different answers, leaving astronomers scratching their heads. Quasars, with their extreme brightness and sheer distance, provide a unique workaround. By studying how their light interacts with intervening galaxies and gas clouds, scientists can map the universe's expansion history with surprising precision. One clever trick involves quasars paired with gravitational lenses. When a massive galaxy bends a quasar's light into multiple images, the time delays between those images depend on the universe's expansion rate. It's like cosmic stopwatch: the longer the delay, the faster the universe is growing. Other methods use quasars as backlights, illuminating the vast web of gas between galaxies. By analyzing how this gas absorbs the quasar's light at different distances, researchers can track how expansion has changed over billions of years. What makes quasars so valuable is their sheer range. They're visible across nearly the entire age of the universe, filling in gaps where other cosmic yardsticks, like supernova, fall short. And while the Hubble tension isn't solved yet, quasars are narrowing the gap, offering clues that might one day reconcile the conflicting measurements. So next time you hear about the universe's expansion, remember, quasars aren't just dazzling cosmic lighthouses. They're also helping us measure the very fabric of spacetime itself. Now let's unravel another fascinating layer of quasar science: polarization. Light from quasars doesn't just travel in straight lines. It can also carry hidden clues about the extreme environments around these cosmic powerhouses. When we study how quasar light is polarized, we're essentially decoding the fingerprints of magnetic fields in their jets and accretion disks. Here's how it works. Polarization happens when light waves vibrate in a specific direction, often influenced by magnetic fields. For quasars, this means their light can reveal the structure and strength of magnetic fields near the supermassive black hole. Imagine it like looking through polarized sunglasses. The glare is reduced because certain light waves are filtered out. In quasars, that glare tells us about the chaos swirling around the black hole. The jets blasting out from quasars are especially rich in polarized light. These jets, made of particles racing at nearly the speed of light, are threaded with powerful magnetic fields that twist and shape their paths. By measuring polarization, astronomers can map these fields, uncovering how they accelerate particles to such incredible energies. Even the accretion disk, the swirling maelstrom of gas feeding the black hole, leaves its mark in polarized light, hinting at how magnetic turbulence heats the disk to millions of degrees. What's truly mind-blowing is how polarization can even help us see regions otherwise hidden from view. Some quasars are so shrouded in dust that their cores are invisible in ordinary light. But polarized light sneaks through, carrying secrets from deep inside. It's like having X-ray vision for the cosmos, peeling back layers to expose the heart of these distant monsters. So next time you hear about quasar light, remember, it's not just about brightness or color. the subtle dance of polarization opens a window into the invisible forces shaping some of the most violent and energetic places in the universe. Now, let's turn our attention to one of the most violent cosmic spectacles imaginable: tidal disruption events. These cataclysmic moments occur when a star ventures too close to a supermassive black hole, like those lurking at the heart of quasars. The black hole's immense gravity stretches and shreds the star in a process called spaghettification, creating a brilliant flare of light that can outshine an entire galaxy for months. What makes this even more fascinating is how quasars might be connected to these events. While quasars are powered by steady streams of gas falling into their black holes, tidal disruptions offer a sudden, explosive feast. Imagine a black hole that's been quietly snacking on gas clouds suddenly getting a massive stellar buffet. The resulting flare could temporarily supercharge the quasar's activity. Some astronomers suspect that rare, ultra-bright quasars might actually be black holes in the middle of devouring a star, giving us a front-row seat to cosmic destruction. These disruptions don't just light up the sky, they also leave behind clues. As the star's material swirls into the black hole, it forms a temporary accretion disk glowing fiercely across X-rays and radio waves. By studying these signals, scientists can measure the black hole's mass and spin, almost like taking its fingerprint. And in some cases, the debris from the shredded star might even fuel the quasar's jets, sending fresh bursts of particles screaming across space at near light speed. Here's the wild part: tidal disruption events might help explain why some quasars flicker unpredictably. While most quasars shine steadily thanks to their gas-rich diets, a sudden stellar snack could cause a dramatic flare, making the quasar appear to wake up or dim erratically. It's a reminder that even the most powerful objects in the universe can have chaotic, explosive moments, and quasars, it seems, are no exception. So next time you hear about a distant quasar flaring unexpectedly, remember, it might not just be a routine burst of energy. There's a chance a star just met its spectacular end, torn apart by a black hole's insatiable hunger, and lighting up the cosmos in its final act. Now, shifting our cosmic lens to a broader perspective, let's unpack one of the most revealing tools in astronomy: the quasar luminosity function. Think of it as a cosmic census that tracks how quasars of different brightness levels are distributed across the universe and how their numbers have changed over billions of years. This isn't just a dry catalog, it's a dynamic record of the universe's most energetic adolescence. Picture this: as astronomers map quasars from the early universe to the present day, they've noticed a striking pattern. The brightest quasars were far more common around 10 billion years ago, during what's often called the quasar epoch. Back then, the universe was a crowded, chaotic place, with galaxies frequently colliding and funneling vast amounts of gas into their central black holes. This golden age of quasars saw these objects shining at their peak, lighting up the cosmos like beacons in the dark. But here's where it gets even more intriguing. The luminosity function reveals that as the universe aged, quasars didn't just fade evenly, they dimmed in a specific way. The number of ultra-bright quasars dropped dramatically, while fainter ones became relatively more common. This shift hints at a cosmic fuel crisis. Over time, galaxies ran out of the dense gas needed to feed their black holes at the same furious pace. Without this steady diet, the quasars' engines sputtered and their brilliance waned. What's truly remarkable is how this function acts like a time machine. By measuring the brightness and distribution of quasars at different distances, and thus different eras, scientists can reconstruct the history of black hole growth and galaxy evolution. It's as if each quasar's light carries a timestamp, revealing not just its own story, but the story of the universe itself. So the next time you gaze at a quasar's distant glow, remember, its brightness isn't just a number. It's a clue to the universe's past, a piece of a puzzle that shows how the cosmos transformed from a fiery, quasar-filled youth into the quieter, more mature expanse we see today. Now, let's tackle one of the universe's great detective stories, the case of the missing baryons. You might think astronomers have a pretty good handle on all the ordinary matter in the cosmos, but here's the twist: about half of it has been unaccounted for. That's where quasars come in, acting like cosmic flashlights to reveal this hidden material. The missing baryon problem is like realizing you've only tallied half the ingredients in a recipe. We know how much normal matter, protons, neutrons, and electrons should exist based on the early universe's conditions. But when astronomers add up all the visible stars, galaxies, and gas, the numbers don't match. The rest, it's lurking in vast, diffuse clouds of warm, hot intergalactic gas, too faint to see directly. Quasars are the perfect tool for uncovering this elusive matter. As their light travels billions of light years to reach us, it passes through these invisible gas clouds. Each cloud leaves a fingerprint-specific absorption lines in the quasar's spectrum, like barcodes revealing the gas's composition and temperature. By studying thousands of quasars, astronomers have mapped this cosmic web of hidden matter, showing it's woven between galaxies in a delicate, filamentary structure. What's fascinating is how this gas stays hidden. It's not cold enough to form stars or dense enough to glow brightly, but it's too hot to be detected by traditional telescopes. Only the piercing light of quasars, combined with sensitive instruments, can expose it. These discoveries don't just solve a cosmic accounting problem, they show how the universe's large-scale structure is built, with quasars illuminating the scaffolding that holds it all together. So next time you hear about the universe's missing matter, remember, quasars are the ultimate sleuths, shining a light on the shadows of the cosmos. Now, let's zoom in on one of the most extreme environments in the universe, the chaotic whirlpool of matter surrounding a quasar's supermassive black hole. Picture a cosmic blender spinning at nearly the speed of light, where gas and dust don't just fall in smoothly but spiral violently into oblivion. This is the accretion disk, and its physics are nothing short of mind-bending. At these distances from the black hole, gravity isn't just strong, it's ferocious. The friction between particles in the disk heats them to millions of degrees, turning the disk into a seething ocean of plasma so hot it glows with X-rays. To put that in perspective, the sun's surface is a chilly 5,000 degrees Celsius by comparison. This heat isn't just a byproduct, it's the engine behind a quasar's blinding luminosity, converting matter into energy with terrifying efficiency. But here's where it gets even wilder. The disk isn't a flat, orderly pancake, it's warped, turbulent, and threaded with magnetic fields that twist like spaghetti in a hurricane. These fields channel some of the infalling material into those high-speed jets we've talked about, shooting particles across galaxies. Meanwhile, the inner edge of the disk marks the point of no return, the event horizon, where even light surrenders to the black hole's grip. What's truly astonishing is how much we've learned by studying these disks. Their flickering light tells us about their size. Some are as vast as our solar system, while their spectra reveal compositions ranging from hydrogen to heavy metals forged in stellar explosions. They're not just feeding the black hole, they're recycling the universe's raw materials on a colossal scale. So next time you hear about a quasar's brilliance, remember, it's not just the black hole at work. It's the physics of this churning, superheated maelstrom that turns quasars into the universe's ultimate power plants. Now, let's tackle one of the most puzzling quirks of quasars, their tendency to break the cosmic rules. Normally, a black hole's appetite has a speed limit, a point where the radiation blasting outward from its meal should push back hard enough to stop more material from falling in. This balancing act is called the Eddington limit, and it's like a cosmic traffic light telling the black hole, no more gas for now. But quasars don't always play by the rules. Some of them blast past this limit, shining brighter than physics says they should. Imagine a car not just speeding but somehow ignoring air resistance entirely. That's the kind of defiance we're talking about. Astronomers think these overachievers might be gulping down matter so fast that the infalling gas piles up in a way that lets the black hole temporarily cheat the system. It's like stuffing a pizza into your mouth faster than you can chew, creating a messy but effective workaround. What's even wilder, these limit-breaking quasars might be key to solving the mystery of how supermassive black holes grew so big so early in the universe's history. If they can binge feed beyond the Eddington limit, even for short bursts, it would explain how these cosmic monsters packed on billions of suns worth of mass in what, by cosmic standards, was basically a lunch break. So next time you hear about a quasar outshining entire galaxies, remember, some of them aren't just powerful, they're cosmic rebels bending the laws of physics to their will. Now let's pull back the cosmic curtain on quasars that play hide and seek with us. Not all of these brilliant beacons are visible in plain sight. Some lurk behind thick veils of dust completely invisible to optical telescopes. Imagine trying to spot a lighthouse through a dense fog. That's the challenge astronomers face with these obscured quasars. But here's the clever part. While dust blocks visible light, it can't hide everything. Infrared and X-ray telescopes cut through the cosmic smokescreen, revealing quasars that would otherwise stay hidden. Infrared light, with its longer wavelengths, slips past dust particles like a whisper through a closed door, while X-rays punch straight through, exposing the fiery heart of these obscured monsters. Why does this matter? Because counting quasars only in visible light would miss a huge chunk of the story. These hidden giants might be just as common as their visible cousins, meaning we've underestimated how many quasars are really out there. Some theories even suggest that obscured quasars are a key phase in a black hole's life, when it's feasting so violently that the surrounding dust hasn't yet been blown away by its fury. So next time you picture a quasar blazing across the universe, remember, some of the most fascinating ones are the ones we can't see until we look in the right light. Now let's turn our attention to an invisible dance happening across the cosmos, one where quasars leave their mark on the oldest light in the universe. The cosmic microwave background, that faint afterglow of the Big Bang, carries subtle fingerprints of quasars through something called the Sunyaev-Zeldovich effect. Here's how it works. When the intense radiation from a quasar plows through the hot gas surrounding galaxy clusters, it gives electrons in that gas an extra kick of energy. These supercharged electrons then bump into the ancient microwave background photons, shifting their energy ever so slightly. Modern telescopes, like the Atacama Cosmology Telescope or the Planck satellite, can detect these tiny distortions, like spotting ripples from a pebble thrown into a pond long after the splash. This effect isn't just a cosmic curiosity, it's a powerful tool. By studying these imprints, astronomers can map where quasars have heated the universe's hidden gas, revealing the invisible scaffolding of galaxy clusters and the vast cosmic web. What's truly mind-bending, this interaction lets us see quasars in a way no telescope ever could, by the shadows they cast on the oldest light in existence. It's a reminder that even the most distant, energetic objects in the universe are part of a grand, interconnected story, one written in the whispers of microwaves and the echoes of quasars long gone. But here's something that might twist your understanding of quasars even further. Some of these cosmic powerhouses aren't flying solo. Imagine two supermassive black holes, each billions of times heavier than our Sun, locked in a gravitational dance at the heart of a quasar. These are quasar binary systems, and they're some of the most extreme partnerships in the universe. Astronomers have spotted these duos by detecting subtle wobbles in the light of quasars, a telltale sign that not one but two black holes are pulling on each other as they orbit. Some of these pairs are separated by just a few light years, close enough that their gravitational waves, ripples in space-time, might one day be detectable with future observatories. What's even wilder, these binary systems are essentially previews of colossal galaxy mergers. When two galaxies collide, their central black holes eventually sink toward each other, and if they get close enough, they can form a quasar with a double engine. Over millions of years, these black holes will spiral closer, eventually merging in an explosion of energy that would outshine an entire galaxy. Finding these systems isn't just about witnessing cosmic chaos, it's a clue to how galaxies grow and evolve. Every quasar binary we discover is a snapshot of a future collision, a reminder that even the mightiest objects in the universe are bound by gravity's relentless pull. And who knows, the next one we find might be on the verge of creating the loudest splash in the cosmic pond. Now, let's turn our gaze closer to home, because even our own Milky Way might hold clues about quasars. You've probably heard of the Fermi bubbles, those enormous, mysterious structures stretching tens of thousands of light years above and below our galaxy's center. They're like two giant balloons of gamma-ray energy, and no one's entirely sure what created them. But here's where it gets interesting. Some scientists think quasars might hold the answer. Imagine, billions of years ago, the supermassive black hole at the heart of the Milky Way could have been a quasar, feasting on gas and blasting out jets of energy. If that's true, the Fermi bubbles might be the fading echo of that ancient outburst, a relic from when our galaxy was far more active. It's like finding an old campfire and realizing it was once a roaring blaze. There's another twist. Some researchers suggest these bubbles could have been inflated by multiple smaller eruptions, not just one big quasar-like event. Either way, studying them gives us a front-row seat to how black holes shape their surroundings, even long after their brightest days are over. And if quasars really did leave their mark on our galaxy, it means these distant cosmic beacons aren't just faraway wonders. They might have shaped the very sky we see today. So next time you look up at the night sky, remember those faint gamma-ray bubbles might be the ghostly handiwork of a quasar that once called the Milky Way home. Here's how we can map the unseen using quasar light echoes to reveal the hidden architecture of cosmic dust clouds. Picture a quasar's brilliant flash of light racing through space, only to bounce off dust particles like a cosmic ping-pong ball. These delayed reflections, called light echoes, act as probes, letting astronomers trace the shape and density of otherwise invisible dust structures. Think of it like shining a flashlight into a foggy room. The way the light scatters tells you where the mist is thickest. When a quasar flares up, its light doesn't just travel straight to us. Some of it takes detours, ricocheting off dust clouds at different distances. By measuring the time lag between the initial burst and these secondary glows, scientists can reconstruct a three-dimensional map of the dust's distribution. This technique has unveiled staggering details like vast, intricate filaments of dust weaving around quasars, or colossal shells of material ejected by ancient galactic collisions. Sometimes these echoes even reveal dust clouds so faint they'd be utterly invisible without the quasar's borrowed light. It's a bit like hearing an echo in a canyon and using it to guess the shape of the cliffs. What's truly remarkable is how these echoes bridge time and space. The light we're catching might have left the quasar centuries before the echo finally reaches us, offering a layered snapshot of its surroundings across different eras. So while quasars themselves are fleeting beacons, their echoes linger, sketching a hidden blueprint of the universe's dusty back alleys. And with that, we're ready to unravel another quasar mystery, one written in the delicate tracery of ancient gas clouds. Now let's peel back another layer of the quasar mystery, this time hidden in the ghostly fingerprints of ancient gas clouds. When astronomers point their telescopes at a distant quasar, they don't just see a single beam of light. Instead, the quasar's spectrum reveals something astonishing, a dense thicket of absorption lines known as the Lyman alpha forest. Think of it like holding a flashlight behind a frosted glass window covered in countless smudges. Each smudge represents a cloud of hydrogen gas floating between the quasar and us, absorbing specific wavelengths of light. The farther away the cloud, the more its light is stretched by the expansion of the universe, shifting its absorption line toward redder colors. This creates a forest of lines, some faint, some bold, stacked across the spectrum. Each one is a snapshot of a gas cloud at a different distance, effectively giving us a core sample of the universe's structure. The closer the lines are packed together, the denser the cosmic web in that region. Some of these clouds are remnants of the primordial universe, barely changed since the first stars flickered to life. What's truly mind-bending is how these wispy filaments trace the skeleton of the cosmos. The Lyman alpha forest reveals where matter clumps into galaxies and where vast voids stretch empty for millions of light years. It's like reading tree rings, but instead of years, each line tells the story of gas drifting through space for billions of years. And just as forests change with the seasons, this cosmic one evolves too. Early in the universe, the lines are packed tight, reflecting a younger, denser cosmos. Later, as galaxies form and intergalactic gas thins, the forest grows sparser. By studying these patterns, astronomers can track how the universe's structure unfolded over time, all thanks to quasars shining through the cosmic fog. Now, imagine turning these ghostly traces into a map, one that charts the invisible scaffolding of the universe itself. That's the power of the Lyman alpha forest. Now let's shift our gaze to how these brilliant cosmic lighthouses do more than just dazzle us. They illuminate the darkest corners of the universe. Quasars aren't just spectacular to observe. They serve as indispensable tools for astronomers, acting like celestial flashlights in the void. Their intense light pierces through cosmic fog, revealing secrets about dark matter, the expansion of space, and even the distribution of galaxies across billions of light years. Think of quasars as nature's ultimate backlight. When their radiation passes through vast clouds of dark matter, the invisible scaffolding of the universe, it subtly bends, a phenomenon called gravitational lensing. By studying these distortions, scientists can map the unseen dark matter that makes up most of the universe's mass. Without quasars, we'd be stumbling in the dark, quite literally. But their usefulness doesn't stop there. Quasars also help measure how fast the universe is expanding. Remember those absorption lines in the Lyman alpha forest? The spacing between them changes over cosmic time, acting like a ruler stretched by the universe's growth. By comparing quasars at different distances, astronomers can track how expansion rates have shifted over billions of years, key evidence in the ongoing debate about the Hubble constant. And here's something even more mind-blowing. Quasars help locate the universe's missing matter. Turns out, about half the normal atoms in the cosmos are hiding in warm, diffuse gas between galaxies too faint to see directly. But when quasar light passes through these regions, it gets imprinted with telltale absorption signatures, allowing scientists to finally account for this elusive material. So next time you hear about a distant quasar, remember, it's not just a faraway curiosity. It's a beacon guiding us through the universe's greatest mysteries, from the ghostly pull of dark matter to the relentless stretch of space itself. And with every new quasar discovered, the cosmic map we're piecing together gets a little clearer. Now let's peer into the future and see how the next generation of telescopes will unlock even more secrets of these distant cosmic powerhouses. The James Webb Space Telescope, already dazzling us with its breathtaking images, is just getting started when it comes to quasar research. With its infrared eyes, Webb can cut through cosmic dust like never before, revealing quasars so ancient their light has been stretched into the infrared by the expansion of the universe. This means we'll finally get a clear view of the very first quasars, those that ignited when the universe was barely out of its infancy. But Webb isn't alone in this quest. Upcoming giants like the extremely large telescope with its 39-meter mirror will capture details in quasar host galaxies we've never seen before. Imagine resolving the chaotic dance of gas and stars around a supermassive black hole in real time. Meanwhile, the Square Kilometre Array radio telescope will map quasar jets with unprecedented precision, showing us how these particle beams sculpt their surroundings across millions of light years. And here's the game changer: these telescopes won't just observe quasars in isolation. By combining their powers, astronomers will create a multi-wavelength portrait of these objects, from radio waves to X-rays. This holistic approach could solve long-standing mysteries, like how quasars regulate star formation in their host galaxies, or what exactly triggers their explosive outbursts. The future of quasar studies isn't just about sharper images, it's about rewriting cosmic history. With these technological marvels coming online, we're on the verge of seeing the universe's most energetic objects in ways that would have seemed like science fiction just a decade ago. Every new observation will bring us closer to understanding how quasars shape the cosmos, and perhaps even reveal surprises that will force us to rethink what we know about black holes, galaxies, and the evolution of everything. Now let's shift our gaze to an exciting frontier: how quasars might be whispering secrets not just through light, but through cosmic messengers we're only beginning to decode. Picture this: a single quasar could be firing off more than just dazzling beams of radiation. Some might also blast out ghostly particles called neutrinos, or ripple spacetime itself with gravitational waves. These signals could be the missing pieces in our puzzle, helping us see quasars in ways light alone can't reveal. Neutrinos, those nearly weightless particles that slip through planets like they're not even there, might originate in the chaotic hearts of quasars. When detectors like IceCube in Antarctica catch a high-energy neutrino, astronomers sometimes trace its path back to a distant quasar, hinting at a violent event, perhaps matter torn apart near the black hole's edge. It's like getting a postcard from the universe's most extreme environments, written in a language we're just learning to read. Then there's gravitational waves, the echoes of colossal cosmic collisions. While we've mostly detected waves from merging black holes or neutron stars, some theorists suggest quasars could produce their own faint tremors, maybe from clashing gas clouds in their accretion disks, or even binary supermassive black holes spiraling toward a merger. Future observatories like the Laser Interferometer Space Antenna might one day pick up these subtle quasar quakes, giving us a whole new way to study their inner turmoil. What makes this multi-messenger approach so thrilling? It's like upgrading from a silent movie to surround sound. Light shows us the fireworks, but neutrinos and gravitational waves could reveal the engine behind the explosion. The hidden mechanics of how quasars devour matter, accelerate particles, and warp spacetime. Every new signal is a chance to test our theories, and who knows, the universe might have a few surprises waiting in these invisible whispers. So as telescopes and detectors join forces, we're not just watching quasars, we're listening to them, feeling their vibrations, and piecing together a story that's written across every wavelength and particle the cosmos can send our way. Now let's take a step back from the science for a moment and explore how these cosmic powerhouses have sparked the human imagination. Quasars, with their enigmatic name and otherworldly nature, have become a favorite muse for science fiction writers and creators. The word itself, quasar, sounds like something ripped straight from a futuristic saga, blending mystery and grandeur into just 2 syllables. It's no wonder they've been cast as everything from alien energy sources to apocalyptic weapons in stories across books, films, and games. Think about it: a quasar's sheer power, outshining entire galaxies, makes it the perfect plot device for tales of advanced civilizations or cosmic threats. In some sci-fi universes, quasars are gateways to other dimensions, their intense radiation bending reality itself. Others imagine them as ancient beacons left by long-vanished aliens, their light carrying encoded messages across billions of years. Even their unpredictable flickering has inspired stories where quasars behave like living entities pulsing with intent. Then there's the eerie beauty of their imagery. The swirling accretion disks, the jets stretching across light years, It's visual gold for filmmakers and artists. From the glowing cores of fictional starships to the backdrops of alien worlds, quasars add a touch of cosmic awe to any scene. And let's not forget their role in video games, where they might power superweapons or serve as navigational hazards in sprawling space adventures. But perhaps the most fascinating thing is how quasars blur the line between science and myth. Long before we understood them as black hole-powered dynamos, their mysterious light sparked legends among early astronomers. Today, they continue to fuel our curiosity, reminding us that the universe's most dramatic phenomena often inspire its most creative stories. Whether as a scientific marvel or a storytelling trope, quasars prove that the cosmos is the ultimate source of wonder both for our telescopes and our imaginations. Next up, we'll ponder the ultimate fate of these celestial giants and what they might leave behind in the far, far future. Now let's peer into the distant future, not just billions but trillions of years ahead, to uncover the ultimate fate of quasars. These brilliant beacons, which once dominated the early cosmos, won't shine forever. As the universe expands and evolves, the era of quasars will slowly draw to a close. The reason? They'll simply run out of fuel. Quasars thrive on chaos galactic collisions, swirling gas clouds, and vast reservoirs of matter falling into their supermassive black holes. But over time, the universe grows quieter. Galaxies drift apart, star formation dwindles, and the gas needed to power quasars becomes scarce. Without fresh material to feed their accretion disks, these cosmic engines will sputter out, their dazzling light fading into darkness. What remains will be the silent skeletons of their former glory, dormant supermassive black holes lurking at the centers of aging galaxies. No more jets, no more radiation, just immense gravity wells, cold and inactive. Even the black holes themselves won't last eternally. Over incomprehensible timescales, they'll slowly evaporate through Hawking radiation, leaving behind nothing but faint whispers of their existence. It's a poetic end for the universe's most luminous objects. The quasars that once reigned supreme, shaping galaxies and lighting up the cosmic dawn, will become relics of a bygone era. Yet their legacy endures, the heavy elements they forged, the galaxies they sculpted, even the light still traveling across space, all of it carries their story forward. So while the age of quasars will one day pass, their mark on the cosmos is forever. And with that, we've reached the end of our journey through 50 mind-bending facts about quasars. From their explosive births to their quiet fade into history, these cosmic marvels remind us just how dynamic and fleeting the universe can be. If this deep dive left you as awestruck as we are, don't forget to like, subscribe, and hit that notification bell for more cosmic adventures. Until next time, keep looking up. As we wrap up this cosmic journey, let's take a moment to reflect on the sheer scale and significance of quasars. These distant beacons aren't just dazzling lights in the void, they're cosmic storytellers, revealing secrets about the universe's infancy, the growth of supermassive black holes, and even the structure of space itself. From powering the reionization of the early universe to sculpting galaxies with their fierce winds, quasars have left an indelible mark on the cosmos. Their brilliance, visible across billions of light years, reminds us how small yet connected we are in this vast expanse. Every flicker, every jet, every whisper of light carries clues about the forces that shaped everything we see today. And while the era of quasars will one day fade, their legacy, etched into the fabric of the universe, endures. So what do you think? Did any of these 50 facts about quasars leave you awestruck? Maybe you're curious about how we detect them or what future telescopes might reveal. Drop your thoughts and questions in the comments below. We'd love to keep the conversation going. And if you enjoyed this deep dive into the universe's most distant powerhouses, don't forget to like, subscribe, and hit that notification bell so you never miss another cosmic adventure. Until next time, keep exploring, keep wondering, and remember, the universe's greatest mysteries are still out there waiting to be uncovered.